Good afternoon, everyone. Welcome to the talk. The topic of today's talk is parse machine learning through hierarchical matrices which have a lower rank structure. So let's get started. So the problem here is to develop fast algorithms for kernel-based machine learning. So I'll be addressing this problem in today's talk through these examples, that is in applications, the following applications. I'll talk about kernel-based SVM and Gaussian process regression, and then highlight the scope of improvement, that is where to improve the computational complexity and how to do it. So I'll be briefly stating the mathematical formulations of these two methods. I'll not go in detail of the mathematical formulations, as we all know as we all must have studied them in one of the machine learning courses. So let's get started with SVM, the basic one, which is called as a linear SVM. So the task here we have is to do classification. So you have a cluster of points, say this, all of these belong to class 1, and all of these green points, say they are cluster 2, and say they belong to class 0. So when I have a linearly separable data, I can model a line here or a hyperplane, and the equation of that hyperplane. So here I'm only plotting it in 2D, so therefore this is a line. So when in 1D, I'll be constructing a hyperplane that separates the two classes. So I'll model this line as W transpose X plus B is 0. And correspondingly, I also model the top margin here, with represented here on dashed line, and also the bottom margin. And the goal here is I want to construct these two margins such that the perpendicular distance between these two margins is maximized. So I can then state an optimization problem in the following manner, wherein my goal is to maximize this margin or the perpendicular distance, and it is inversely proportional to norm of W square. So I state my optimization problem as minimizing norm W square because this corresponds to maximizing this margin. Subject to what are the constraints? The constraints are here that all of these points which belong to say class 1, they should be lying on or above the right margin. And similarly, the second cluster of points should be lying on or below the lower margin here. And that mathematically translates to this condition. So this is the regular or the linear SVM formulation. And the same problem has its dual written using the Lagrange multipliers alphas. So the same problem can also be stated in its dual form with this as the objective function, where the optimization variables now are alphas and subject to this constraint. Correspondingly, the decision rule is f of x is the sign of this evaluation. So let me not go in detail of how I constructed this, but let's say that using the KKT conditions and using the Lagrange multipliers, I have formulated this optimization problem. Now, the limitation here is that we can only do this if the data is linearly separable. What if the data is non-linearly separable? Say in this case, if you see the data points, the blue ones and the green ones cannot be separated by any line that you draw on this plane. So we then use the kernel trick to be able to separate this class 0 and class 1 points. And the kernel trick is that each point in this lower dimensional space, in this example it's in 2D, each point in 2D is mapped to some point in 3D. So I introduce the third variable along this, and I then represent each of these points, or I map each of these points in this 3-dimensional space. So once I move to 3-dimensional space, I can here then develop a hyperplane or model a hyperplane that can separate the two classes of points. So moving to this higher dimension space is being modeled in this fashion. That is, you're going to map each xi to some phi of xi. So xi here belongs to say R2 and phi xi belongs to R3. So in this example, so in general, you map to some higher dimensional vector. And if you go back to this dual formulation, you see the terms xi transpose xj here, as well as in the decision rule, you have xi transpose x. So what will these terms then be? Xi transpose xj, it becomes phi xi transpose phi xj. And now I define a kernel function k evaluated at xi comma xj. So this is defined as the dot product between phi xi and phi xj. So instead of making phi as our unknown, I can directly make k as the unknown, or k, I can model directly k. Why? Because I only have always x's in dot product terms. So xi transpose xj here, and here as well I have xi transpose x. So I don't have to model phi. Instead, I can directly model k xi xj, which is defined as phi xi transpose phi xj. And typical kernel functions that are used in SVM are, that is, you can define this kernel function to be a linear function, which gives us the linear SVM model. You can also define the kernel function as a polynomial, or using the radial basis function, which is this e power minus norm x minus y whole square by 2 sigma square. Or you can also model k to be a tan h function. And here on the left, you can see various scenarios of non-linearly separable data and how each of these kernel functions is able to separate them out. So now let's go back to the mathematical formulation which we have looked at in the previous slide, the dual form. So the dual problem had this objective. So I have replaced the xi transpose xj with k xi xj. And these are my constraints, and this is the decision rule. So I therefore have to solve a constrained optimization problem here. Now this is the way I solve it. I use gradient descent. In gradient descent, the objective function that I consider is whatever objective function I have in the dual problem minus some penalty I assign on these constraints. So whatever is the constraint that we have, sigma I equal to 1 to n alpha I yi, I take the square of it and multiply it with beta. Beta here is a positive hyperparameter, and I put a negation here. So when I try to maximize this function, this term also gets maximized, but here I have a minus sign, meaning this term gets minimized. Beta is positive, so the model tries to minimize the squared term, or it tries to make the minimum it can go is it tries to make it 0. So automatically this constraint can be enforced. So I therefore introduce a penalty term for the constraint and put it in the objective function itself. So this is my unconstrained objective function now. And I can then use gradient descent. How? I'll update my alphas. Alphas are my unknowns here. So I need to update alphas. Let eta be the learning rate, and dou L by dou alpha I is the gradient of L with respect to alpha I. So, and that term, dou L by dou alpha I, takes this form. You have to take a partial derivative of this expression with respect to alpha I. And that is what I've written here. And this is just one term in the gradient of L. We also need the other terms. So, or in other words, we need the entire gradient vector. So let me write down the vectorized form. So here dl of alpha represents the gradient of L with respect to alpha. And this is the vectorized form of this expression. So here y is a vector, k is a matrix, and v is a vector. What is k? K is nothing but a kernel matrix. So whatever kernel function we have assumed, let that be k, and I'm evaluating that function at x1 comma x1, x1 comma x2, and so on, x1 comma xn. Similarly, the other rows. So I have an n cross n matrix appearing in this expression of gradient. So, and here dot star, I'm using the MATLAB notation to represent the element wise dot product. So this is a vector multiplied element wise with this vector. KV is a vector. So with element wise vector multiplication minus beta. So this is also an operation on a vector, summing of elements in that vector times a vector y. So if you see here, this is a vector operation. Y dot star is also a vector operation. And here you have k times v. So this k times v computation takes order n square evaluations, or it takes order n square floating point operations. And that is the most computationally expensive operation involved in finding out this gradient, because the rest of the terms are just vector operations and they can be done in O of n time. But this k times v, which is a matrix vector product, it will take O of n square time. So that is the main or the highest time taking task in the gradient descent of this problem. So let me pause with SVM here and move on to another application, Gaussian process regression. So before moving on, let's summarize what we have seen till now. That I have an optimization problem and I have modeled it using gradient, I've solved it using gradient descent, and I see a matrix operation, a matrix vector product, which takes O of n square. So my goal is to reduce it to O of n or O of n log n. How I do it, I'll explain it after a few slides. But before that, let me also state the problem of Gaussian process regression, just to motivate ourselves why this kernel matrix operations are important. So in Gaussian process regression, our task is to learn an unknown function f, and we are given this training data. So x1, y1, x2, y2, and so on, x and yn are given. And we want to develop a regression or model a regression problem. But here, the observations yi are not just f of xi, but they involve some noise term as well. So here, my training data involves some x's, which are these features, and the corresponding observations. So the observations are coming from some function f of xi, but there is also some added noise to it. So my observations involve fxi added with some noise added to it. And I'm going to model this noise using Gaussian distribution with mean 0 and variance sigma square. So let's look at this figure. So here, if you see, there is a dotted red curve, which is the actual function f of x equal to x sin x, and which is not known to us. But we are given some observations, that is observations of this form, that unknown function f plus some noise added to it. Those observations are given, and I'm going to represent those observations here using small vertical line segments. And why do we have this vertical line segments instead of a dot? Because of this noise term. The noise term can take up values coming from this distribution, and so therefore I can have observations on these line segments. So my goal is here to model f of x. But this is not like a L2 regression problem wherein you model your f to be a linear function with some parameters. So I'm not going to model f in a parametric form with some unknown parameters, but the way I model it is that I consider f to be coming from some distribution, and I find that distribution. So instead of modeling f as f in a parametric form, I model its distribution. That is, I find its distribution. I'm going to say that if a new x star is given to me, I'll tell what distribution f x star belongs to. I'm going to find the distribution of f x star. So that is what we do in Gaussian process regression. So let's go into the mathematical formulation of it. I'll construct some f of here capital X, the x in bold represents that it is a vector. So f of x is a vector of function values evaluated at all of the training data points that I have. And I'm assuming some prior distribution on f of x, I'll assume that f of x is coming from this Gaussian distribution. This is a prior I'm assuming that f of x belongs to this Gaussian distribution with zero mean and covariance matrix K. So this is a prior distribution I'm assuming before even looking at the data. And the covariance matrix K, its entries take this form. So I'm going to define the covariance matrix in the following fashion. The ijth entry of the covariance matrix is some kernel evaluation. K represents the kernel evaluation at xi and xj. And here again, typical kernels that we use in Gaussian process regression are the RBF kernel or the Laplace kernel or the inverse quadratic kernel. So let's summarize what we have till now. I have a prior over the training data, that is f is being considered to be coming from this distribution, Gaussian with zero mean and covariance matrix. So this means that kx or x comma x means that I'm evaluating a covariance matrix of size n cross n, where n is the number of training points I have. And that covariance matrix, its entries are the evaluation of the kernel function. And where will you evaluate it? At the training, at pairwise, you take pairwise samples of your training data set and you fill up the matrix of size n cross n. So that is this covariance matrix. And what is y? Y is the observation. Y follows f plus epsilon. Y is f plus epsilon. And epsilon is a Gaussian with zero mean and sigma square variance. All epsilons are IIDs. So this y is this f plus some epsilon. So therefore, it is also Gaussian. And its mean is 0. F's mean is 0 and epsilon's mean is also 0. So this mean is 0. And F's covariance matrix is kx comma x. And sigma square is the covariance of the noise that I'm considering. So therefore, this vector y will have k plus sigma square I as the covariance matrix, where I here is the identity matrix. And what do I do in prediction or in testing? If a new point x star is given to me, I'm going to find the distribution of f x star. That is, let me represent f of x star as f star. So I'm going to find the distribution of f star. And since I have taken the prior on f to be of Gaussian, zero mean and this covariance, I can similarly consider f star to also belong to Gaussian distribution with zero mean and variance. What is a variance term? It's nothing but again the kernel function evaluation at x star comma x star. So this is the knowledge I have from the prior data, from the prior distribution, that is before seeing the data. Now I'll find out what is a joint probability distribution between y and f star. So if I know that y is Gaussian, f star is a Gaussian, I can say that y and f star also follows a Gaussian distribution. And both the y's mean and f star's mean is 0. So here I have a 0 term. And y has this as the covariance matrix. So here comes the covariance matrix of y. And f star has this as the variance. So correspondingly here I have this as the variance term. And the covariance between the x's corresponding to this y and x star. So this is a row vector evaluated at x, capital X comma x star. And similarly, here I have the covariance between x star and x. So this is the joint distribution I have between y and f star. Now, after seeing the data, I change my assumption or I update my assumption and make the posterior distribution. So f star given y, given that I have seen y, I'm going to modify my f star. That is f star given y, this is the conditional distribution and I'm going to find it from this joint distribution. So if you know the joint distribution between two random variables, you can find the conditional distribution by working out the maths, and you can show that this is a Gaussian distribution with some mean and variance, where the mean takes this form and the variance takes this form. So the summary is that if I'm given a new x star, I'll say what f star given y is. That is, I'll say what the distribution of f star. The f star or f of x star belongs to this Gaussian distribution with mean mu star, and this is the variance. So that is the reason here in this figure, I don't predict just one point for a given x star, but I predict a band of values. So this is the band. If this is the x star that I'm if I want to find f x star at this point, then this is the band, or this is the uncertainty region that I also specify in addition to the mean of that distribution. So I say what the mean is, and I also say what the standard deviation is. So I can therefore say with this much confidence, my f star will lie in this range. Okay, so let's come to the computational part. So here, this is a vector, kx star x is a row vector. This is a matrix, kx comma x plus sigma square I is a matrix, and its size is n cross n. If you have n training points, then you have the size of this is n cross n. You need to invert it, then multiply it with n cross 1 matrix. So inverting n cross n matrix is a computationally expensive task. Or in other words, you need to solve this system, kx comma x plus sigma square I, some x equal to y. So you need to solve some ax equal to b kind of a system here. So this therefore is a computationally expensive task. Why? Because the number of floating point operations involved here is big O of n cube. If n is the size of the matrix, it takes big O of n cube number of computations. Similarly, even here, while finding sigma star, you need to invert the matrix and multiply it with this vector. So again, you have O of n cube operations, and the corresponding matrix here has the term coming from the kernel function. So here there is a lot of scope to improve the speed of the algorithm or the computational complexity. And the goal here is to reduce this computational complexity from n cube to n. Yes, yes. So earlier in SVM, we had this KV term, n cross n matrix times V. That is an n square operation computation. And now in the Gaussian process regression, we had mu star written out in this fashion, where you need to invert it and multiply it with y. So this again involves here n cube operation. In SVM, the highest complexity is coming from matrix vector product, and here it's coming from the inversion. So this costs order n square, and this costs order n cube. And common kernel functions used in SVM are these, and in Gaussian process regression we have these. So so this is called as the RBF kernel. This is the Laplace kernel. This is the rational quadratic kernel. This is a polynomial kernel. So now that we have stated two problems where there is a scope for improvement, let's see how we actually improve the speed. So to know how to improve the speed, we need to know what this function, what this matrix is, how this matrix is built. That is, in constructing the matrix, I'm evaluating some kernel function. So are there some properties of the kernel function that I can leverage or take advantage of and speed up my computations? So let's try to understand kernel functions in more detail, and later on we'll use some properties of that to improve our speed. So let me be working only in 1D, though this whole explanation holds for any dimension. So I consider x comma y to belong to real numbers, and I then assume that I have a kernel function that is smooth and analytic. So I need a smooth kernel function. The reason is because I am now going to construct the Taylor series approximation, the Taylor series expansion of kx comma y. So to construct the Taylor series, you'll need the partial derivatives with respect to the partial derivatives of order m, and here m goes from 0 to infinity. So to be able to say that I have all the higher order derivatives, I need the function k to be smooth. And to be able to say that this series converges to kx comma y, I need the function k to be analytic. So under those assumptions, let me write down kx comma y as this Taylor series expansion. And here I'm expanding the Taylor series about y naught. I'm not expanding about x. For a fixed x, I'm only expanding about y naught and writing down the Taylor series. So if you carefully see here, the first part here, this part, is only a function of x. And the second half is only a function of y. So I can therefore write this as summation over m equal to 0 to infinity, some psi m function which only depends on x, and some psi m function which only depends on y. So I have phi m of x multiplied with psi m of y, and I have infinite such terms. So now let's see how these functions behave, the phi m and psi m, how these functions behave. So from now on, I assume that x is far from y and y is close to y naught. I consider that x is far from y, meaning the difference between x and y is huge, and y is close to y naught, meaning y minus y naught is close to 0. Under these assumptions, I'm now going to study how phi m behaves. So as m grows, phi m of x decays. So let's numerically justify it. So I have plotted on x-axis x and on y-axis phi m of x for various m's. And I have considered x far from y and y close to y naught. It means that x is far from y naught. So here I'm considering y naught to be 0, and I'll consider x is far from y naught 0. So x is far from y naught 0 means in this range or in this range. So if you see in this region, m decays a lot, and sorry, phi m decays, and the decay is even higher for higher values of m. So in these regions, the values of phi m's are very low. So let's take the takeaway from this figure is that phi m's as m grows is it has a very low value. Yeah. Why? No, for just plotting it, I've just taken, there is no other reason for m being odd or even. Yeah, so that's the conclusion we have, that as m increases, phi m decays. And let's now look at psi m of y. So I have assumed y close to y naught. So y minus y naught is a very small value, and here m is positive integers. So as m increases, so small value taken to the power of m, this value decreases. So even psi m decays as m increases. So there exists some finite r such that I can truncate all the higher order terms. So if I can just approximate this infinite series summation that I had here, I can truncate it after r terms, because beyond certain r, the values are very less. So therefore, I'm going to approximate it with a finite number of terms or a r term series expansion. So the summary till now is, when x and y are well separated, or when x and y are far, or if x and y belong to clusters that are very well separated, then this kernel function takes the separable representation. If you see, the variables got separated into two functions. So this is called as a separable representation of in R terms. Now let's vectorize this equation. That is, I just don't want to evaluate at one x and one y, but I want the complete matrix because I see these such matrices appearing in these algorithms. So I'm now going to evaluate this kernel function at x1, x2, and so on xn cross y1, y2, and so on yn. Meaning I'll pairwise evaluate at x1, y1, x1, y2, and so on x1, yn. That is, I'm going to construct this matrix. And here on the right, I have two matrices. So from this equation, I'm writing out this equivalent equation in terms of matrices. So if you see kx1, y1, how is it found? You multiply this row with this column. So phi1 x1, psi1 y1 plus phi2 x2, phi1, phi2 x1, phi2 y1, and so on. And that gives this summation term. And that holds true for any ijth entry here. So if you carefully see here, the first column is the evaluation of function phi1. Second column is evaluation of phi2. And the rth column is evaluation of function phi r. So these form the column basis. Each of these functions form the column basis of this matrix K. And here I have first row to be psi1, second row is evaluation of psi2, and so on. So each row here corresponds to the row basis of this matrix. And let's now look at the dimensions. So here I have n cross n, and n is the number of training data points that I have. And n can go large if you have a large training data set. And this I have approximated by writing it in two factors, that is an n cross r matrix and an r cross n matrix. Yes. Yeah, we want r to be not dependent on an r to be O of 1. That's when the complexity gets reduced. So we will see that. So what is the rank of this approximation, or what is the rank of this matrix? If you write an n cross n matrix as n cross r times r cross n, the rank is r. Now we'll see how this rank r compares to the value n. Now let's jump to some numerical experiments. So I have, I'm in 1D, that is I have just one feature in my training data set, and I'm plotting those features. I'm just doing a scatter plot, putting those feature values in 0 to 1. So I have n such points. And I'm going to now construct a matrix with this as the definition of the ijth entry. And why have I considered this? If you remember, in the Gaussian process regression, we had the matrix K plus sigma square I. So it is the same definition I'm also using here. I'm exactly constructing the matrix that we have seen in Gaussian process regression. So now I will find out what the rank of Kij is numerically. So what is the definition of rank? So rank is number of non-zero singular values. But when you're working on a computer, you always define some tolerance, and the number of singular values that are larger than that tolerance, you define it as your rank. So here, I'm considering different values for n, meaning I'm constructing matrices of these sizes, and I'm plotting the decay of singular values. So on x-axis, I have the singular value index, and on y-axis, I'm plotting the singular values. Or I'm here actually plotting the normalized singular values. So what are normalized singular values? If I divide each of the singular values with the largest singular value, I get the normalized singular values. Why do I want to divide it with the largest singular value? Because always when we work on computers, we work in relative sense. We define relative errors. So therefore, in a relative sense, I'm now going to define what my rank is. If the normalized singular values, the number of normalized singular values greater than this tolerance is what I define my rank as. So I define rank as the number of normalized singular values greater than the tolerance that you set. Here I've set 10 power minus 6 as tolerance. And now let's see n equal to 128. So n equal to 128, the singular values were decaying like this. And for n equal to 2048, the singular values decayed like this. And this was the last singular value. So meaning all of the singular values, say for n equal to 2048, I have 2048 singular values and all of them are above the threshold. So therefore, I have my rank to be equal to n. So the inference from this is that whatever n you take, the rank is always equal to n in this scenario wherein x's and y's are same. What are x's and y's? The points where you actually evaluate your kernel function, k of x comma y. So if x's and y's are same in the evaluation of your kernel matrix, then the rank of that matrix is always full, or it's a full rank matrix. Now let's look at this scenario wherein I place my x's in this region and y's in this region. That is, I consider this as say cluster 1 and this as cluster 2. So here cluster 1 and 2 are separated, and I again repeat the same experiment. That is, I construct a kernel matrix and then I find the singular values and plot them. So here if you see, at around 6, that is say after the 7th singular value, all of the singular values have values lower than the threshold. So I only have 7 singular values above the threshold, therefore the rank is 7. So the inference is that if x and y's are separated and I construct a matrix in that scenario, the rank of that matrix is low rank. And you see that the rank is always 7 irrespective of the size of the matrix. And such ranks are called as low ranks. That is, it does not depend on n. Now let's take on one more example where I put even farther away the y's. So here are the y's and here are x's. And here is how the singular values decay. So at around 5, meaning I have 5 singular values above my threshold. So therefore, I define the rank here as 5. So here again, the inference is same. If the clusters are well separated, then the corresponding kernel matrix interaction is low rank. And farther the clusters, lesser is your rank. Okay, we have discussed about the rank of the matrix and why are we studying whether it's low rank or whether it's full rank. So let's understand this. So if you have a low rank matrix, say if R is very much less than N, then what advantage do you get in computations? Say suppose you have a matrix A, which is of size n cross n, and say it has a low rank, then it can be factorized as UV transpose. And U size is n cross R, V transpose size is R cross N. So here I pictorially represent that. I take a matrix, I write its factors U and V. So here U is a thin matrix and V transpose is a fat matrix. Now let's see what a matrix, what is a computational complexity of matrix vector product when done on this matrix. That is, I multiply a vector to this matrix, but instead of multiplying directly, I multiply it to the low rank factorization. That is, I write U V transpose times that vector. So first, what you do is you multiply V transpose with, say X is this vector, V transpose X is what you multiply. And the cost of that is, what is V transpose size? The size of V transpose is R cross N. So therefore, the number of operations in this matrix vector product is big O of Rn. And once you have this resultant, you then multiply this resultant with this matrix. And the size of that matrix is n cross R. So n cross R matrix, you are multiplying with R cross 1 vector. And its cost is again O of Rn. So this step costed as O of Rn, this times this, as well as this times this also costed as O of Rn. So in total, the computational complexity is O of Rn. And if R is small, if R is not comparable to n, if R is like O of 1, then you can write O of Rn as O of n. So this is the advantage you get when you know that a matrix is low rank and you want to do a matrix vector product. Further, from what to what have we reduced the computational complexity? If you had done the matrix vector product naively on this matrix, it would have costed you O of n square. So from O of n square, I have come down to O of Rn. And how did I do that? By knowing that the matrix is low rank, I've written it in UV transpose, and this is the reduction that I have got. Now let's move back to the kernel matrix that we had seen in the previous applications, and let's see if this matrix is low rank. If it is low rank, then I can speed up my matrix vector product. So I say I have this, I'm again working in 1D, though this is applicable to any dimension. So I'm considering a 1D domain, and I have some training data points, that is I have some features distributed in this domain, and correspondingly I have my kernel matrix. This is my kernel matrix I'm showing here on the right. And how do you find out this kernel matrix? It is kx comma x. X is x comma x. Both the x's are the same data points actually. So therefore, those points are not separable. If you have x comma y, and if both x and y are well separated, then the corresponding matrix that you have is low rank. But since that the points here are x, and the way you construct this covariance matrix is k of x comma x. You evaluate at the same points itself. So therefore, according to the numerical justification that we have previously seen, if the clusters are not separable, then you have a full rank matrix. So I therefore represent this in red to illustrate that this is a full rank matrix. Now, can we do better on this? Let's look at that. I have this domain. Let me divide it into two subdomains. So I divide it at the midpoint. So this is, say, cluster 0, and this I call as cluster 1. So when I divide my domain into two subdomains, correspondingly the matrix gets divided into two by two subblocks. So this particular submatrix corresponds to 0, 0 interaction. This corresponds to the interaction between the points in this and the points in this. Similarly, this corresponds to the interaction between points in this cluster and points in this cluster. And this is interaction between points in this cluster with itself. So if you carefully see, 0, 0 is the self interaction. So its rank is full. So I plot it in red. And 0, 1 and 1, 0, they are separated out. So they have a low rank. And I represent a low rank submatrix in cyan here. And we can even go further and subdivide each of these subdomains. Say I have now 4 subdomains. So let me retain this low rank block as it is here, and let's concentrate on this full rank subblock, 0, the one corresponding to 0, 0. So when you subdivide it further, you can say that this cluster is well separated to this cluster. So out of this red block, you can then say that this small cyan colored block is low rank. Why? Because 0 and 1 are separable. Similarly, this is also low rank because 1, 0 is separable. Similarly, 2, 3, 3, 2 are these blocks. So these are again low rank. So this way of refinement can be made in a scalable manner. That is, you can go even further, extend the levels, and you see this kind of a low rank structure appearing. So matrices which have this kind of a low rank structure, a hierarchical low rank structure, that is, you're dividing your domain hierarchically and you're seeing a hierarchical low rank structure appearing in the matrix. So that these matrices are therefore called as hierarchical matrices. And this hierarchical matrix structure holds true for the kernel functions that mostly we'll be using in kernel-based machine learning. For example, the RBF kernel or the Laplace kernel, all of those kernel matrices follow this structure. So when I say that a particular matrix is low rank, I can represent it using its low rank factorization. Meaning this whole submatrix is low rank, so I can represent it as some U S V transpose. And the reason I have shown it to be thin is it only has R columns, R being the rank of this matrix. So wherever I have a low rank, instead of storing this whole matrix and say n by 2 cross n by 2, I'll only be storing these three matrices. Similarly here. So wherever there is a low rank, memory wise, the complexity gets reduced because the number of terms in USV transpose is lower compared to the total number of terms in this matrix. So that is the way I store it in computer. And now let's look at the time complexity of matrix vector product in using this structure. So whatever is my last matrix at the highest level that I have constructed, I'm going to take that and I'm going to represent it as sum of these three matrices. So in the first matrix, I have the terms coming from the level 1, the low rank blocks from level 1. These are the low rank blocks from level 2, plus you have the full rank blocks. So I've just represented it as sum of three matrices. And my original matrix, the matrix that I have in the kernel-based MLs, that matrix is A, that is approximated using this kernel matrix, and that kernel matrix, I'm representing it using some of these three matrices. So when I say that these are low rank, I can represent them with some USV transposes. And using some rearrangement, I can rearrange these things in this manner and state that this matrix is actually equal to U1 S1 V1 transpose. So I place this green blocks in this manner, this red blocks as this right diagonal blocks, and this purple blocks as this diagonal blocks, and I call them as U1 S1 V1 transpose. So it's just some rearrangement. When you actually multiply these three matrices, you get back this matrix. And similarly, I rearrange some terms and create these three matrices, and this is actually equal to this. And I call this as the A full because these are the full rank blocks. So what I have is the kernel matrix A is approximated as summation over L equal to 1 to 2 Y2, because in this example I've gone till level 2. If it is level L, I'll have L here. And in the summation, I have UL, SL, VL transpose plus A full. So this is how I can approximate my kernel matrix. Now let's look at the complexity of matrix vector product if I use this structure. That is, if I approximate my kernel matrix into this low rank structure, what is the complexity? So let's evaluate the cause. That is, I need to multiply this matrix with a vector. So instead of multiplying it with this matrix, I multiply it with this matrix plus I multiply it with this matrix plus I multiply it with this matrix. Because AX is nothing but A1X plus A2X plus A3X. So now let's look at each of the individual terms. Say this is level 1, this is level 2. So at level L, what is the cost? Let's look at that. The number of blocks here is 2, and this is level 1. The number of blocks here is 4, and this is level 2. So in a generalized manner, number of blocks at level L is 2 per L. If you're working in 1D. And each block is of size. So for here, you have n by 2 cross n by 2 as the block size, n by 2 cross n by 2. Whereas this block size is n by 4 cross n by 4. So in a generalized manner, each block size is of n by 2L cross n by 2L. And each of these blocks are low rank. Let it be R. So then what is the cost of multiplying one such block with the corresponding vector? So if I multiply this submatrix with a vector here, what is the cost? The cost of multiplying each subblock of this size and of rank R is n by 2L cross R. Why? We have earlier seen multiplying an n cross n matrix of rank R is O of Rn. And here we have this as the size of the block and its rank is R. So therefore the cost is NR, N by 2L cross R. And this is multiplying one sub block, say this block. So the total cost is multiplying all the sub blocks. So I need to therefore multiply it with the number of blocks 2 power L. So I have NR as the cost for multiplying this matrix. Similarly, this matrix NR. Now let's see what is the cost of multiplying this matrix. So how many full blocks are there here? Full rank blocks. The number of full rank blocks is 2 power L. If L is the largest level that you have gone to, then 2 power L number of blocks are there. And typically you choose L to be O of log n. In that case, the number of blocks grows as O of n. And the block size is n by 2 power L cross n by 2 power L. The cost of multiplying this full rank matrix is n by 2 power L cross n by 2 power L. Because this is a full rank matrix, so its cost is going to be order. If you have an n cross n matrix, multiplying it costs order n square. So here you have n by 2 power L cross n by 2 power L sized matrix. So its cost of matrix vector product is this. And you have 2 power L such blocks. So you multiply 2 power L times this. And this simplifies to n as your cost for multiplying this matrix. So let's now look at the total cost. This is the cost we have at level L, and we have L such levels. So I take summation over L equal to 1 to capital L NR plus the last matrix. The cost of matrix vector product with this is n. So and here L goes from 1 to L. Here L is assumed that we go till log n levels. So here therefore I have NR L plus n, and L is log n. So I substitute it and I get it as O of Rn log n. And R typically, as we have seen in the example, R is very less compared to n. So you can say therefore, you can therefore conclude that you have an n log n matrix vector product algorithm for kernel matrices and machine learning. So the conclusion is, if you have done it naively, you will have order n square, but using hierarchical matrices, you will have it as O of n log n. And this is one way of constructing the hierarchical matrix, what I have shown. There are even better ways of constructing hierarchical matrices, which will give us even better complexity. That is, we can even go to O of n. Similarly, I'll not explain the solver part, but the naive solver takes O of n cube, but the hierarchical matrix based solver can do the solve this Ax equal to b in O of n log square n time. And there are even better hierarchical matrix structures than what I have shown today, and they will end up in giving you O of n complexity. So these are some of the results for the matrix vector product versus n. So this red line here shows the naive complexity, and the blue line here is what you get if you approximate your matrix with hierarchical matrix. And similarly, the solve time. The red one is the naive complexity, and the blue one here corresponds to the one which you get if you had used the hierarchical matrix structure. So let's look at in very brief manner a few open problems which we can work on by using what we have seen till now. PDE solvers. So what are PDEs? Partial differential equations. Say for example, you have a Poisson equation, del square u is fx. The solution to u using integral equations from scientific computing methods, you can write it down as integral over some k x comma y f y dy. F here is known. So what is the problem here? The problem here is f is given and you want to find u. And the equation that's given is del square u is f, where x belongs to some domain. So this is a Poisson equation problem. And one way of solving it is expressing u as integral equation integral over kx comma y. So for every partial differential equation, there exists something called as a Green's function defined as k. And the Green's function for this particular Poisson equation is 1 over norm x minus y. Even this function obeys whatever we have discussed till now. That is, if you construct a matrix coming out of this function, the matrix can be approximated using the hierarchical matrix structure. Why? Because this is a decaying function, and at towards the end, that is, as you go away from your x equal to y, away from the singularity, the function is very smooth and decays. So therefore, this function can also be represented using a rank R approximation. And when I discretize this integral, I have summation over j equal to 1 to n, this term. And when I represent it in a matrix vector format, where u is evaluated at some x1s to xn's, I have it as the structure. So here again I have an n cross n matrix where each matrix entry is evaluation of this kernel function. So I can therefore solve Poisson equations using better algorithms, say O of n algorithm or O of n log n algorithm, if I approximate this kernel matrix using hierarchical matrix structures. And one interesting way of solving this is another interesting way of solving this is using neural networks. So this is what you do algebraically. But suppose if you want to do it using neural networks, so here the inputs are this f's, fy1, fy2, and so on, fyn, and you construct a feed-forward neural network, and at the outputs you have u1, u2, and so on, un. So if you construct a feed-forward neural network, the number of parameters here are going to be n square. But since that we know from the maths that this is a kernel function evaluation and this has a low rank property, therefore I don't need n square parameters here. I'll only need O of n log n parameters. So therefore the number of parameters can be reduced, and correspondingly the time it takes to train and the inference time also gets reduced. So by leveraging the property that you know that this kernel matrix can be low rank approximated, you can even speed up the neural networks constructed to solve PDEs. And one more application that in which we can use the hierarchical matrix structures and vision transformers. So in every transformer, we have this self-attention layer in the encoder part. So let's look at what happens when you give an image as input to your encoder. So what you do is you divide your image into, say, n cross n patches, and each patch is then fed to this encoder part, and it then finds the attention between these patches. So that is what happens in the lowest part of your encoder model, or the self-attention part. That is, you're going to split this image into n patches, and then you find a attention matrix A, which takes this form softmax of q k transpose by root over d, where the query vector constitutes q, and this is the key values. And you have this attention matrix. So what does Aij represent here? How much attention the ith patch is getting from the jth patch. So that is what Aij represents here. And this problem is interesting, particularly when you have large n. That is, if you're working in high resolution, when you're working on high resolution images, the size of the matrix A is going to be huge. A n cross n, where n is the number of patches. So if you're working with 4K images, the size is going to be large. And in such cases, the computations involved with matrix A involves O of n square for matrix vector product, O of n cube for solvers. So such computations can be speeded up or can be accelerated if we approximate A with hierarchical matrix structure. But how do we say that? How do we justify that A follows the hierarchical matrix structure? Because since that we are working with images, the structure is as follows: that nearby patches are highly correlated. In an image, there is a lot of local information that, say, if you consider one particular patch here, it interacts strongly with its neighboring patches than it interacts with the far away. So therefore, the nearby patches are highly correlated and you have strong interactions. And the distant patches are weakly correlated or they have the low rank interactions. So when you properly write down the matrix structure, that is, when you write down the A matrix, then you see that the diagonal blocks are dense blocks because they are the self interactions, and the off diagonal blocks are the far away interactions and they interact very weakly or they can be low rank approximated. So therefore we can again have the same kind of structure which we have seen earlier, that is the diagonal blocks are full rank and the off diagonal blocks are low rank. So it therefore fits very well to the hierarchical matrix structure that we have seen, and all of these off diagonal blocks can be low rank approximated. And so therefore, if you recursively do this partitioning and construct a hierarchical, and you can construct a hierarchical matrix structure. So the benefit as again from O of n square to O of n or O of n log n. So the conclusion is, in kernel-based machine learning, we encounter kernel matrices, and these kernel matrices have this very nice low-rank structure, which can be leveraged to speed up computations. In matrix vector products, the computational speed goes from n squared to n, and for solvers, it goes from n cubed to n. And this is not limited to kernel-based machine learning. So wherever you have an n cross n interaction matrix, where you have local interactions to be strong and far away interactions to be weak, you can, even in such scenarios, you can approximate your matrix with a hierarchical matrix structure. Yeah, that's the conclusion. Thank you.